I'm Steve McLaughlin, Dean of the Georgia Tech College of Engineering, and this is The Uncommon Engineer.
We're just absolutely pleased as punk to have you with us. Please say a few words.
In many developing nations across the world, drinking water and sewage system infrastructures are non-existent. This leads to unsafe sanitation issues causing public health concerns. To fix this, the Bill and Melinda Gates Foundation challenged top scientists and engineers to build a better toilet that doesn't require running water. Welcome to another episode of the Uncommon Engineer podcast. I'm Steve McLaughlin, Dean of the Georgia Tech College of Engineering. The Uncommon Engineer discusses how Georgia Tech engineers make a difference in our world, in our daily lives, in ways you might not expect. Our guest today is Dr. Shannon Yee. He's a professor in the Woodruff School of Mechanical Engineering here at Georgia Tech. His research is focused around thermodynamics and energy transfer. He's taking that knowledge and trying to develop a toilet that uses heat transfer to break down wastes instead of water. Welcome to the program, Shannon.
Thank you. It's great to be here.
Yeah, well, we're really happy to have you. Today we're going to talk about toilets. A lot of people, it's a topic a lot of people don't want to talk about. A lot of people aren't necessarily familiar with. It's something we take for granted in the U.S. and in Europe, but why are foundations like the Gates Foundation and yourself working on toilets?
Yeah, I think the short answer is there's a lot of individuals out there who do not have access to improved sanitation. If you break it down, there's about 2.5 billion people around the planet who don't get to enjoy the luxuries that we have when it comes to sanitation. It's also a major global disease vector. I don't think people realize that about 80% of feces end up in water, which is why we spend so much energy and resources cleaning up water so we can drink it. If you can keep feces out of water to begin with, then we have an easier job later. It really is a problem for everybody, is the short answer. The developing world is of particular interest because of pathogenic vectors. But even for the developed world, our sanitation systems are about 100 years old, and they're aging pretty rapidly right now. When we look at it, we probably are looking to do some massive replacements of that infrastructure over the next 30 to 50 years. What I worry about is I don't think people realize how expensive those infrastructure improvements are going to be. And in some cases, even in the developed world, we may not be able to afford that.
So, yeah. And so before we get into some details, the image that just brought to mind is, even in the most developed countries, something that, so in the less developed world, I can imagine toilets that are kind of self-contained. Don't require plumbing or don't require sophisticated plumbing like we have. And I think you're saying, kind of more modular or single unit kinds of things. And you're saying maybe even in the developed world, because of all this decaying infrastructure, that kind of model might work for us too. We don't necessarily need to be tied to the infrastructure we have, and it may be a big advantage. And I know that you've received a large award from the Bill and Melinda Gates Foundation, which I think a lot of people are familiar with. Mm-hmm. So maybe talk kind of what are the specific challenges that the Gates Foundation is interested in, and which the challenges that you're addressing in your lab?
Yeah. So the overall challenge for the Gates Foundation project is to deliver a sanitation system that is very low cost. And the cost that we're looking at is about 5 cents per user per day as kind of a generic cost. When I break that down to an individual toilet, it comes out to a CapEx cost about $450 for the unit, with an operational expense cost about 15 cents per day. So those are the cost targets we're looking at. And when you translate that, that becomes affordable then to the developing world. It comes in at about 3.75 cents per user per day with those targets. That's one of the major drivers. The major technical specifications we have to hit are really holistically trying to limit oral fecal pathways. So how do we actually prevent oral fecal contamination? Right?
So
yeah, how do we
I know
do
it's a little uncomfortable to talk about, but feces that ends up in the water that ends up being consumed.
That's exactly right.
Yeah.
Yep. In our current infrastructure, we rely on mixing feces with water. We have we have flush toilets, right? And then everything goes down a pipe, and you forget about it, right? And so we use water primarily as a transport mechanism to these centralized facilities. However, when you look globally, where population growth is currently predicted, a lot of the fecal sludge management, about 74% of the fecal sludge management zones are actually in areas where water is a scarce resource. So how do you start treating waste without water? And that's why there's a need to move away from a centralized system and look at how you can do it in a distributed system.
Well, this certainly can't be a new problem. I'm sure society, we've known this for a long time, decades, if not hundreds of years. And so I'm really curious about what the challenges are, kind of getting to this point, and what the Gates challenge that you're involved in, what it's addressing.
Yeah, most certainly. So you're right. It's not a new problem. People have been having to deal with their waste for quite a long time. What have been facing over the last, let's say, 100 years, maybe a little more, is we see a kind of a dense urbanization. Right, we have people moving towards cities. And so with that, we had kind of the advent of the flush toilet and the S-trap and the P-trap, which has really modernized a lot of our sewage infrastructure. And that occurred right around 1900s. So it's been about 100 years now since we've seen a kind of a reimagination of that system. And so about a decade ago, the Gates Foundation realized this and said, you know what, we need to help nucleate a change in how we look at sanitation, right? And so up until that point, I would say the field was really kind of stagnating. There weren't really new inventions to come to that were developed. So back in 2010, 2011, the Reinvent the Toilet Challenge was launched in 2011, and with that, a whole bunch of grantees came to try to work on this problem. And over the last 9 years, those grantees have been nurtured, and there's now more of a scientific community. There are a couple new ideas and patents, and there's some different prototypes that have been developed around the world to address this problem. And what we're looking at here, and the question I posed to the Gates Foundation, have we done enough science to really deploy engineering at scale? And I think this is where Georgia Tech comes in as a unique partner with this, because we can really start bringing together many different disciplines. And with our strengths with the Georgia Tech Research Institute, we can really pull that team together. Where we are now is we're trying to be hyper collaborative, and it's not a competition. We're not trying to compete against each other to see who has the best idea. We're now trying to look holistically across the entire portfolio and go, what ideas work best? Because not all the best ideas originated at one group.
Yeah.
There are really great ideas with multiple different groups, and how can we pull the best ideas and then collaboratively come together with a really ideal solution?
I'm ready to hear about some of the interesting ideas and solutions, or the ones that you're working on, or the ones that you're most excited about, or where you think it's headed.
Definitely. We're still in the early phases of this. We kicked everything off in May. And what we're doing in this first 12-month period is we're having a series of design workshops where we're evaluating the different modules, so the different concepts that come through. The first design workshop we had was to look at the overall system. Right? What choices do we want to make about how the system is going to work, because that will influence the individual modules. At the end of this month, we're gathering everybody in Switzerland, and we're taking a look at specifically the fecal processing module. And there are numerous ideas for how we can actually do the fecal processing. They're largely, or at least I largely categorize them into 3 buckets. One we refer to as wet oxidation, one I refer to as gaseous oxidation, and one that I refer to as rapid oxidation. For the case of gaseous oxidation, that's kind of like drying everything and then combusting the feces. So that's been the dominant choice for a lot of the portfolio to date. And so we want to take a look at that and see, okay, is it on the right cost trajectory? Can we manage a stable flame or a smoldering front at such a small scale? What we've learned to this point is that combustion works, but it works at a slightly larger scale than the individual toilet. And so we're still trying to evaluate, are there unique engineering solutions that allow us to get it down to that individual toilet scale? Right? When it comes to wet oxidation, I kind of refer to this as we're trying to burn underwater. Right? Well, we're not actually burning anything underwater. We're going through an oxidative process in the presence of water. Right? And there have been other groups that have looked at this. There's been a couple universities, a couple national labs, and that process is largely categorized into kind of three areas that we're looking at. One is subcritical wet oxidation. Another one is supercritical wet oxidation, where we operate at temperatures and pressures higher than the critical point for water. And the third one is what's known as hydrothermal carbonization, where we actually increase the temperature and pressure to a point where we start getting polymerization, as the short answer. We actually get carbonization, so the mass just starts forming long polymer-like chains. And so we're evaluating different modules right now and different processes that will go into this overall system. I think what makes this process different than any of the previous attempts is we really are focused on separating the streams up front, right? So we have different modules for processing urine than we have for processing feces, than we have for processing flush water, right? So we look at processing those in different ways. They have different energy demands on them. And by processing three separate streams, we think we can get to a lower cost, lower energy system. For this problem, right, if we want to achieve low cost, we really have to achieve a highly energy efficient system, right? So focusing on heat transfer and thermodynamics really allows us to be on a trajectory to achieve a low cost system. And it's just really making decision choices based upon thermodynamics and heat transfer that really, I think, make this a unique system and a unique approach.
And I assume there's a cultural element that you must be thinking about for toilets. So I know we're off topic, but I'm really curious about that.
Not a problem. So there's a very prolific YouTube video where Bill Gates was drinking water out of one of these processes, right? There are ways that you can take it to potable levels, right? The best way I can think of is if you combust everything, one of the combustion products is water vapor, and then you can condense that water vapor. It's kind of like a fancy distillation process. So it's possible, but I really think it depends on the business case and the cultural acceptance for that specific region. Because the solution, when we think of a toilet, it's not just one solution, right? One thing I've really, maybe I shouldn't admit to this, but one thing I've enjoyed is now when I travel, I look at the plumbing fixtures around the world, even around the country, right? They're very different. Right? There's all these different styles and different ways of connecting up, and there's unique cultural aspects to every single bathroom, right? And so taking that lesson, just from global observations, we're going to have to come up with multiple prototypes, not just one, right?
I see.
And that's, I think, something that's unique. We're targeting 6 culturally acceptable use cases, right? And why 6, right? When we look at it, we have people around the world who practice wiping and people who practice washing. So wiping is using toilet paper, washing is using anal rinse water, right? We have people around the world who use pedestal toilets, and we have people who use squat plates, right? And we have people around the world who need flush water. They associate flush water with cleanliness, so we need to include flush water. And there are places around the world where flush water is a luxury, and so you may want to use a dry flush alternative, so not using flush water. So that gives us a 2 by 2 by 2 matrix, or 8 different use cases. However, when we look back at it, we don't see a use case for washers who want a dry toilet, because if you're washing, you have water, so you don't want a dry toilet. So that removes 2 use cases. And so when we look at this, we see 6 culturally acceptable use cases. And so we're looking at building 6 different prototypes. Now, a lot of those use cases are on the front end. It's how they interface with the user. And what we can do is we can actually keep a lot of the similar back-end processing. Right? We may have to tweak things based upon separation efficiency or, more toilet paper, less toilet paper, that kind of thing. But the core processing technology can be the same behind the wall. But it's how the users interact and interface with that. Why we're focused on the toilet, if we're really interested in alleviating oral fecal pathways, one of the other things we need to consider is hand washing. Right? It's one of the most effective ways of doing that. One of the challenges here, though, is soap is a really difficult product to use. Right? So if I have to treat soap locally, those surfactants really clog up some of the membranes and it becomes a challenge. When I look at hand washing without soap, the CDC recommends using hand sanitizer. Right? So the CDC recommends using hand sanitizer, and with hand sanitizer, a lot of it is alcohol-based, right? There's been some really good studies looking at, okay, how do we distribute hand sanitizer around the world, right? And in, I guess, use cases in Kenya and Bangladesh, the costs are about $3.70 per liter, right? And when I look at that cost, that would consume about 75% of my OpEx budget just on hand sanitizer. And so when I look at this problem, I'm like, wow, we can't even afford appropriate hand sanitizer. So we need to think of really clever ways at which we can design a hand washing station that can operate and reuse some of that water at very low cost, right? There's other challenges in the bathroom that we have to be aware of. We really have to think holistically. One thing we're looking at treating are feminine hygiene products. So how do we handle those and dispose and sanitize them in an appropriate manner? And then how do we handle family products, diapers, condoms, those kind of things, right? And so looking at all of that, we have to figure out how are we going to address the larger problem. And it's not just the toilet. So those additional auxiliary technologies are also things that we're looking to design in and build as well.
Well, I know some of our listeners will be really curious about the other kinds of cool stuff that's going on in your lab. What kind of stuff do you have happening?
Yeah, so as I mentioned earlier, my lab focuses on energy conversion. So primarily thermal energy conversion. So how do we convert heat to another form of energy like electricity? And the common example that people kind of point to is this concept of thermoelectrics. So thermoelectrics are devices that can take heat and generate electricity without any moving parts, and they can also take electricity and generate cooling. Right? So one thrust for my lab has been developing plastic or polymer thermoelectrics, where the same things you could do with, rigid semiconductors, we can now do with low-cost flexible plastics. I think this is a really exciting area because we've demonstrated a couple of devices. We have one in the Georgia Tech logo that's printed onto a shirt, right? And so your shirt, using these thermoelectric polymers, can convert the heat from your body directly into electricity, which I think is really cool. What I'm more excited about is actually the reverse operation. How do we apply electricity and then deliver personal cooling? Right, so we've done a number of undergraduate student projects with Capstone, developing personal thermostats with a company called Ember Labs, right? Essentially, it's a little thermoelectric device that's connected to a battery that you would wear on your body. The product on the market right now is a little device that goes on your wrist. And what it does is it sends a cold pulse, a cooling sensation to your body to make you feel cooler. So right now they're doing it in a little watch-like architecture. We've helped work with them on developing neck-like architectures. But I'm really excited to see how we could then integrate that more into textiles. So textile integrated thermoelectrics. And then I can give you a shirt. Right? You clip a battery onto that shirt, hit a button, and it can make you feel more comfortable. It can heat you, it can cool you, it can really address the personal comfort challenge. And people look at it and think, oh, this is nifty and neat, but the core problem that it's trying to solve is one I refer to as global cooling. Right? This isn't cooling the planet. This is providing cooling technologies for the world. Right? We just saw a couple weeks ago heat waves in the U.S., right? And we saw sustained heat waves in Europe, and we saw in northern India really sustained heat waves. When I look to the future, we need to be able to deliver low-cost cooling technologies globally. So that's one area my lab focuses on. We develop thermoelectrics for that purpose. We look at electrochemical coolers, how we can do that, magnetocalorics, electrocalorics, thermoacoustics. There's all these different conversion mechanisms that we can use to produce cooling. And it's I think, a need we have for the future.
Super, super cool stuff. I'm really curious about how you found your way to being an engineer. Whether it was as a kid going through elementary, junior high, high school, heading into college. How'd you decide? What's your path to being an engineer?
Yeah, I think I was very lucky, and I would say it found me more than I found it. I always, when I was younger, I always tinkered. Right, I would always build little things or try to modify little things, and I took a lot of things apart, and most of the time I could put them back together, right? And then when I went off to college, I was determined to be a math major because I was really good in math. right? And then the more I thought about it, the more I actually enjoyed applying that knowledge and not just working through it. And so I'm like, okay, what allows me to be very broad, right? And that's how I kind of stumbled across mechanical engineering. When I was going through my courses, it was then the topics associated with energy and heat transfer that really inspired me. And then I like many people, I think I had some really fantastic professors who helped nurture that interest, and they kind of guided me along this trajectory. And then with that trajectory, I got to work on some really large energy projects around the country, and energy is really where I'm focused on.
Well, one of the questions that we ask all of our guests is what makes you an uncommon engineer?
And you're going to first have to tell me what a common engineer is, because when I look at engineers, one trait that I see is they're problem solvers. Right? They go and attack difficult problems. So I don't know if I'm any more uncommon than any other engineer. I like going after and addressing problems. I think the problems that get me most excited are the problems that have large global impact, right? So I want to look at problems that can affect billions of people's lives, or they solve one of the grand challenges that our world is facing. So I get really excited about trying to come up with a contribution or a solution to a really, really large problem. I know a lot of people find that to be very daunting because the problem is so big. I don't think I'm going to solve all of it, but I like trying to figure out what small contribution I can make to a large problem. And that's one of the things I really instill in my students. Is like, okay, you're working on something. Tell me about the motivation. Why? What problem are you solving? What are we actually doing? Right? I think the most precious thing we have is time, and I want to use my time to solve big problems.
Appreciate you being on the show, and most of all, I know I speak for myself and a lot of folks. We're really lucky to have you here at Georgia Tech, and the influence you have on our students and the difference that you're making. And so thanks so much for being here, and see you around.
Yep, my pleasure. Thanks for the invitation.